Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Hi and welcome back to the Neil Ashton podcast. Today's episode is one that is focusing on a topic that I think is interesting to so many people, and that is on supersonic flight, supersonic travel. I'm speaking to Peter Coen, who is a legend within NASA for all that he's done for the supersonic program over the past 3 decades. And I wanted to speak to him firstly because when I spoke to some colleagues and people I work with at NASA, they all recommended to speak to Peter as he is a fountain of knowledge on this program. We didn't really get into actually a focus on him himself. This was more of a topic on the NASA program, although people tell me that he is a private pilot and has some amazing stories to tell. But in this particular episode, we focus more on the actual NASA programs and what they're doing. And that is absolutely fascinating. We start the conversation going back and looking at how did we get to Concorde? You know, that incredible aircraft that was the first to go supersonic for, passenger travel. And then talking, why did it stop? What was the commercial reasons? What was the technical reasons? And then we transition into what makes supersonic travel difficult. What are the engineering challenges from a noise perspective, from a regulatory perspective, from an aerodynamics perspective? And going through step by step in that process. And for anybody here who is an engineer, I think you'll find that particularly interesting. Talking about the specifics of how they overcame some of the issues with the sonic boom. And then we start to go through and talk on the Pacific Quest program. So this is NASA's project to develop a prototype, the X-59 aircraft that is currently in the process of being built. That will be a tester to essentially validate all the work that's been done and to give data to the aviation authorities to be able to set the regulatory environment for commercial entities to go and build and hopefully release these aircraft. So we're at a really interesting time. This project has been going on for quite a while, and it feels like we're getting very close now to some very key tests that will dictate this. And we finish off with some discussion around, of course, hypersonic travel. Of course, if you can do supersonic, the logical question is, couldn't you do hypersonic? And then at the end, as I ask most people on this podcast, some sort of words of wisdom, I guess, to people who are aspiring aeronautics professionals. So this, for me, was personally one of the really interesting episodes. I love the idea of supersonic travel, and Peter is such a great communicator, and it was an honor to have him on the podcast. So sit back and enjoy this episode with Peter Coen on supersonic travel. So maybe we could begin. I mean, this is, I think, for most people, a fascinating topic, but probably the one thing that people think of when we talk about supersonic travel is Concorde. So maybe as a bit of a starter, could you maybe, and I know this is difficult, summarize the history of supersonic travel? How did we get to the Concorde program?
Sure, it's really is. It actually is a fascinating history. I mean, of course, in 1947, we had the first supersonic flight, the Bell X-1, out at what it was then Muroc, or Edwards Air Force Base, and somebody heard a sonic boom then, maybe. So that's a little interesting history, from there, very rapid development of supersonic military aircraft. In the U.S. we had the Century Series fighters, but in Britain there was the Lightning and other supersonic aircraft, and so supersonic flight became pretty common pretty quickly in the 1950s. And pretty much as soon as the basics were understood, people started thinking about, well, we should have, the next step in supersonic travel should be supersonic travel. So there were studies done in all over the world, really, but of course there were English studies. SUD and British Aerospace began working on designs, and eventually came to the common program, the English, the British French program to build the Concorde. So along the way, as supersonic flight became more popular, initially sonic booms were kind of a novelty. They'd do them at air shows, and people would get all excited about them. But as the airplanes began to be used training more and more often, you started having complaints of damage and noise complaints. And when some people really started to think about regular supersonic operations, I think they were thinking of. We really were thinking about the entire air transportation market would become supersonic. And people began to think about the number of overflights that would involve, and the number of sonic boom exposures that people would hear would become a problem. So it led to a number of studies, which involved community tests of people's response to sonic boom. Most notably, there was a very long test with many exposures done in Oklahoma City. In the mid-1960s, but was actually sponsored by the U.S. FAA, and it became quite apparent that regular sonic boom exposure would not be tolerable. So as Concorde development continued, of course, we also had the USSST program, and that's really what drove a lot of the sonic boom testing in the U.S. was trying to understand the impact of the USSST, which was going to be much bigger and potentially much louder in terms of sonic boom than the Concorde. So eventually, Concorde did fly, but and I think it was 1968, maybe 1969 was first flight. Commercial service started in 76, but in between those two times, the FAA put in a ban on supersonic flight over land. There was an idea that if you could quiet the boom enough, you could fly over land supersonic, but they didn't know how quiet it would need to be. So eventually they just said, no supersonic flight means no sonic booms, means nobody's going to get annoyed. So that was in 1973 that ban was put in place. Internationally, there are other countries that ban supersonic flight, but pretty much everybody sticks to what the International Civil Aviation agreed to. Was they didn't put in a law, but or a standard, but they said nobody should experience a negative impact, an unacceptable situation, as they called it, due to sonic boom noise. So, so by the mid-1970s, we had Concorde operations on a very limited scale. And we had all the rules put in place, and that continued into the 2000s when Concorde operations ceased. But the research and trying to understand how to affect the sonic boom, how to make it quieter, and that continued all along through a number of programs.
So was it the case that it was almost a shock to the Concorde developers to have this ban? Because from what I guess, it was imposed after the aircraft had essentially been designed. Was the assumption that they would be allowed to fly anywhere, and then when they put that ban in, it was almost too late to really change the fundamental design or principles?
Yeah, there's a lot to that, actually. I think everybody kind of in the early development of supersonic aircraft, there was very much this is in the U.S., but as globally as well. People thought technology advancement, all technology advancement was good, and that in the 60s that changed, and the advent of sonic boom, the possibility of regular exposure to sonic boom was a part of that change. So, certainly the U.S. manufacturers and British Aerospace and Aerospace Yao, they expected that they would fly over land supersonic, and that the airplanes would be used as regular air transport. So I don't know if it was a shock, but I'm sure they began to realize that sentiment was building against exposing people to this new sound, and it definitely hurt the market, for the aircraft.
I suppose what I'm getting to, because my second question was really why did Concorde ultimately stop and fail in some extent, and I'm just wondering, to that point, was it an economic reason? Was it a technology reason? And is there anything that is essentially because they couldn't fly over land, it just destroyed the economic model? I'm just wondering, what caused Concorde essentially to stop?
I've studied it. I haven't really studied the marketing of it, but there's a couple of things. One of the things that NASA really believes, and kind of the supersonics community believes, that if you're going to have regular supersonic air transportation, the airlines have to be able to operate the airplane as they would any other airplane. So limiting it to just certain overwater routes limits the market and limits the effectiveness of the airplane. So that was a definite strike against Concorde. It was a marvel, essentially the design was pretty much in place, a few years after the first supersonic flight. You had a supersonic airliner, fantastic. But so the technology that was incorporated in it was somewhat immature for airliner technology. And then we had a couple of fuel crises, and then after the accident, there was a downturn, another economic downturn, which kind of limited the operation. So eventually, being able to continue an operation with such a small number of aircraft serving such a small market, I think the airlines basically it was not economically viable for them to continue. So there was regulation, there was technology, and there was economics that all went into I think the end of the Concorde's commercial operations.
Yeah, it is. I've been on Concorde, not when it was flying, but in the museum, and I'm always amazed at how small it is, how tight the seats are compared now, to an aircraft. How and obviously how expensive the tickets were. So it was, I guess as you say, it was a novelty for sure, and I'm sure that helped for a while. But I guess it would be interesting, even if it didn't stop for that reason, would there have been a pressure because of I guess now like first class travel is so much about luxury and the size of the cabins and all this, and you go into Concorde and you're in this tiny little seat.
Yes. Yeah. Well, that's an interesting, again, NASA does studies, and we talk to companies that do studies, and that's a factor. But you look at when given the opportunity to get there sooner, most people will choose sooner in the long run. So
from
NASA's perspective, from NASA's perspective, from the big picture for NASA, we're trying to innovate and do things that improve air travel for the traveling public. And so our mantra is kind of, getting there faster, over long distances is a marked improvement in the experience of the air traveler. So, that's, if we can do that in a way that is affordable, sustainable, and, environmentally acceptable, then if we can put those technologies in place, then, there's a market there that would definitely be of interest to manufacturers.
I mean, it's for sure. I mean, I travel quite a lot to the US for conferences or for meetings, and there is no doubt that the length of time it takes to travel from Europe to the US, I think, does limit how closely those countries can work together. Whereas I know that my US colleagues who have to fly from, let's say, California to Washington, it's still a 6-hour flight, but anything I think less than 5 or 6 hours is a different psychological, different jet lag, different just everything compared to 10 hours or 8 or 10 hours. So I can totally see why the increasing business or closeness, that I'm sure there's economic benefits from making air travel faster. It would promote people to maybe stay in touch more easily.
That's again, that's kind of part of NASA's vision is it makes a smaller world if you can get there in half the time. Yeah.
So what are the high level, as we go towards speaking about the NASA programs, could you maybe just explain to people the high level factors that makes supersonic passenger jets technologically challenging? What is it about the nature of supersonic travel a challenge from a noise point of view, from a fuel efficiency, compared to transonic aircraft?
Well, I mean, we look at as there are barriers, that need to be overcome to make supersonic travel, as I said, economically viable and environmentally acceptable. So we kind of lumped them into categories. One of them is sonic boom. We have to be able to fly over land without disturbing people. So we can talk a little bit more about how we do that, but just for right now, the airplane needs to be shaped to reduce the sound of the sonic boom, and that's not a whole lot different from what a supersonic, what Concorde would look like, but there are some things. To go faster obviously requires more energy. So there's no getting around the fact that it needs more fuel. So, but balancing, the fuel burn at high speed versus the fuel burn at low speed, and getting that integrated design that is efficient as possible, burns as little fuel as possible across the speed regime. That's a key technology challenge. To one of the things that is maybe people don't realize is, current subsonic airplanes have those great big turbofan engines. So they're accelerating a lot of air, just a small amount to create the thrust that they need. And that's both efficient and quiet at subsonic speeds. As you get to higher speeds, your jet has to be faster. You need to accelerate less air more, to create the thrust that you need to go supersonic speed. So you can't have a high bypass turbofan. So coming up with an engine design that matches the requirements of low speed and high speed, but is also for takeoff and landing, can effectively operate quietly. So at the lowest jet velocity, the speed, the jet coming out of the tailpipe, as you can. So that requires some unique engine design. Emissions is a problem. The Mach number of the airplane, the higher the Mach number, the higher you fly. Eventually, you're up in the stratosphere, where the emissions of the engine can have a magnified effect on the ozone layer and the quality of the atmosphere. So, paying attention to how the fuel is burned in the engine, the combustion process, and making a burner, a combustor in the airplane that creates as little emissions as possible is a major challenge for supersonic aircraft. If we go back into the 1990s, when there was the high-speed research program, emissions was one of the big focuses of that effort, and the technology that kind of found its start in that program is now in a lot of the engines that you see on subsonic airplanes. So it's kind of made full circle, and now we're looking at it again. Can we improve it even more to get a bigger impact when we start using those on supersonic aircraft again. So there's that, and there's operations. How do you operate the airplane? How do you mix the fleet together so that the supersonic aircraft can fly as fast as it can for as long as it can, without having an impact on the subsonic traffic. So there's a lot of technology factors that need to be addressed. Airport noise, sonic boom, and emissions are kind of the three real barriers to actually opening the market, I think, to even a supersonic business aircraft.
Well, I'm glad you mentioned that, because that was one of the things I wanted to ask you about. From a conceptual design point of view, when you do the numbers and you figure out the maths on, what's the best size or how many passengers can you put on this thing, what do the sums ultimately drive you to? I'm guessing not a 300-person aircraft like you would see now, but much smaller. So could you maybe talk about how the aircraft design maths work out in that point of view?
You bet. Yeah. So, we're doing the X-59 now. We didn't start out to do a demonstrator. We started out to, in the early 2000s, we had just flown the shaped sonic boom demonstrator and kind of proved that this approach for quieting sonic boom works in a real atmosphere. And there was a lot of kind of innovative thinking going on then about, how we would, how we could advance from where our state of knowledge on quieting sonic boom to really getting to something that was not only worked well, but was what was practical in a design. So we had some ideas. We had new CFD. We had faster computers. We had design systems which enable us to do better optimization. And we really thought we could make a major change in the loudness of a supersonic aircraft. So what we did is we worked with NASA, worked with Boeing and Lockheed in two separate studies to say, okay, if we have this technology and we incorporate it in a future design, what's practical? And what we wound up with was about 100-passenger airplane, so something about the same size as Concorde, that flies at about Mach 1.8, 2 to 3 engines, and 4,500 or so miles range. So trans-Pacific, but barely. That all kind of fit and enabled us to make an airplane that met the boom requirements, met the landing and takeoff noise requirements, and the emissions requirements, and was much more efficient at cruise than Concorde. So those boom shaping technology, the wanting to meet the noise requirements, all kind of, and trying to make the airplane out of materials that don't have to be, we don't have to use special materials for high heat. We have a propulsion system that's balanced for takeoff and landing, and supersonic flight, say about Mach 1.8 is the range, that is the speed that you want to go for. So it's a little slower than Concorde, but it's still twice as fast as current subsonic airliners.
And is that where still you think the sweet spot is in terms of the aircraft, the most practical aircraft? That's what you started off with. Is that still the case, that around 100 passengers, 1.8, is that really what all the sort of analysis studies converge to?
Yeah, there have been more studies, more market studies since then, and just recently we've actually, so there's actually a kind of another community of researchers and companies that are pushing for faster travel, so Mach 4, Mach 5, and so NASA commissioned some more recent studies that since it's kind of being driven by the higher speed community, mm-hmm. we set the Mach range at Mach 2 to 4.5. What's the best answer in that speed range? Well, all the best designs came out to be Mach 2.
Okay.
So what they were kind of saying is, what we really were seeing was those designs were somewhat impractical because they were constrained to be Mach 2. So we felt confident that, if we had stretched that envelope down to Mach 1.7 or so, we would have found even, we would have kind of confirmed our previous results. So the answer is yes. I think generally studies still seem to point to that. Kind of given what we know in terms of technology and given the challenges of higher speed flight, that for the first products that would bring back supersonic flight, that 1.7, 1.8 Mach range is kind of the sweet spot.
Okay, and just to maybe, oh no, please go ahead.
Well, take Boom. Boom Supersonic is trying to build essentially a successor to Concorde. Smaller, but it's kind of that same mission, supersonic over water flight only. They started out, talking about Mach 2.4, and their current design is Mach 1.7. So
okay.
That also kind of confirms where the technology will take you.
Yeah, and just maybe for people's sense, is this? Oh, actually, let's maybe go through. Could you just briefly introduce the NASA program? There is a specific NASA program with a certain name, and so could you maybe just briefly introduce, what is that, and the X-59? I know there's like a specific project, isn't there?
Yes. So again, after we proved this technology to us, at least. So in our Boeing and Lockheed studies, we did designs, conceptual designs. We did a lot of CFD analysis. And then eventually we tested those designs in wind tunnels, so small-scale models, really trying to test. We did a number of tests, but the focus of the test was, did we get the quiet boom design right? And lo and behold, we matched our predictions. Our CFD matched our prediction, our experiment, almost perfectly. So we knew that technology could work. And so there was a lot of excitement about taking the next step. Well, let's try and fly it. But we were very confident in the CFD. So we weren't going to actually prove the technology in flight. We could demonstrate it in flight. But what we learned from flight would be how robust is it? Does it change in different weather conditions? What speed ranges work best? Kind of that information like that, which was exciting science to do, but was not a program that was getting much traction with NASA or with our budget people in the government. In parallel to all this work, we were doing research on how people respond to the sound from supersonic aircraft. So we had done laboratory studies where we built these simulators, which essentially create a sonic boom or a quiet sonic thump, in a lab situation. And we had found that, the numbers that we were getting in our designs, we were able to get to on our designs, were kind of at the threshold where people really almost stopped noticing the sound. So what really sold us was we really wanted to understand how people in a community, going about their daily lives, would respond to the sound. What sound level would be acceptable? And that's where we got the traction. So that's what became the Quests mission, and that's the current big NASA activity. So what we're doing is, and the best way to generate that sound in a community is to use an aircraft that creates a representative sound. So the Quests mission kind of has three phases. The first phase, all phases are active now. The focus right now is building the X-59 aircraft. It's a unique technology. It's a demonstrator aircraft. It's a research aircraft. It's not a prototype for a supersonic airliner, but it does create a sound that's similar to what we think the sounds of the future supersonic aircraft will be. So we're designing that airplane. We've contracted with Lockheed Martin to build the airplane for us. Their contract runs through getting the airplane in the air, doing all the envelope expansion, as we call it, the safety of flight checks, and then they'll essentially hand us the keys, and the airplane will become NASA's property. In the second phase of the effort, we're going to take that airplane. We'll make sure that the sound that we're getting is what we expected. So we call that acoustic validation. Is it loud enough? Can we vary it enough? Is it affected by the atmosphere? Things like that. We really want to understand that sound that we're making, because eventually we want people to hear that sound, and that's phase 3. So in phase 3, we'll take the X-59 and we'll go to different communities. Right now, we've got 5 or 6 tests planned in different places in the United States. We haven't picked those places yet, but we're narrowing it down, if you wish. But so the idea is to expose a community to the sounds of quiet supersonic flight at different noise levels. Have surveys, have microphones in the community to measure the sound. Have people taking surveys to how they respond to the sound. So we can create a data set that describes how, at what sound level is the sound acceptable, and at what sound level is it annoying. In parallel to that, we're working with the International Civil Aviation Organization, particularly their Committee on Aviation and Environmental Protection, because those are the people that write the rules for noise from aircraft. The current regulations for takeoff and landing noise all come from ICAO. They're implemented by, in the UK it's CAA, and in the US it's FAA. But ICAO, all those groups participate in ICAO. They set the standards. So the Quests mission, the main goal of the Quests mission is to give ICAO the data that they can use to set the limit of sound for future supersonic aircraft. So to create that standard that manufacturers could then design airplanes to.
Okay, I see. That's really interesting. So what you're basically saying is, they have to be conservative in nature when it comes to rules. The rules today, that they need as realistic data as possible to make an informed decision, and so what your project will do is help set the foundations, which I then guess when commercial companies like Boom or others want to certify their aircraft, they will be certifying to those noise levels, and I guess a certain distance away and a certain height, and it's all the parameters, I guess, of how they measure it.
So the standard has 3 elements: a metric. So what are you going to measure? What's the best way of measuring the people's response? What number? What process? There's a procedure. So everybody who applies for a type certificate, has to go through the same procedure, so it's consistent. And then there's a limit. What's the value of the metric that you can choose? So the Quest mission really helps to inform all 3 of those elements. We'll be getting a lot of data, so we've got some candidate metrics. We'll be able to test which metric works best. When we're doing that acoustic validation phase, that kind of mimics what the certification process would look like. So we'll be getting data that can help define that certification process, and then when we do the community testing, we'll be actually getting the data that will help support defining the limit. Because NASA can give, we've got a good reputation as being honest, scientific, an honest scientific community. We can give that data. We're pulling in as much of the international community as we can, so that they understand what we're doing. But it's essentially creating that data. But then again, it's up to ICAO and the international community to define what the actual limits and the actual procedure are going to be. So
I'm sure the most difficult question is the timeline of this. So when is the aircraft expect to be handed over to you from Lockheed to be able to start doing some of that validation?
Yes. So we've experienced delays. Very exciting though. We just had our first engine runs. So we've started the engine on the airplane for the first time. So that's kind of a big step forward in kind of the last phase before we fly. We have to do all this really integrated testing where essentially the airplane is completely alive and we're running all the systems and making sure everything's talking to each other. So once we got that done, then of course you do taxi tests first. You drive around on gradually increasing speed, and then you have first flight. So originally we had planned to hopefully do first flight this year, but we've had some delays in getting to the point where we could do the engine run. So now we're looking at sometime next year for first flight. The phase one, this envelope expansion phase is planned for about a year. Mm-hmm. So if things go well, sometime early in 2026, maybe we'll get the keys to the airplane and we'll be able to start our acoustic our acoustic testing.
So would it be fair to say that, realistically, assuming various factors, 2030 could be when the international community could set new rules? They've done all the tests, you've given them all the data, they've debated it, and they've set and written these new rules. Is that approximately, or do you think it could be faster than that?
It's interesting. The CAPE, this Committee on Aviation Environmental Protection, they have a 3-year cycle. So they have a meeting, and at the meeting, all the decisions based on the work that's gone on in the previous 3 years are finalized and accepted and then given to the ICAO Council for final approval. Mm-hmm. So actually, the 13th CAPE cycle is just coming to an end now. So in February of 2025 will be the CAPE 13 meeting. So 2028 is the next one. 2031 is CAPE 15, and that is our target for.
Okay.
That is ICAO's target now for bringing the standard forward to the council for approval. So we are on a timeline to deliver that data. Mm-hmm. To give in a timely enough manner to give them plenty of time to review it, debate it, and finish writing the standard to bring forward at the CAPE 15 meeting in 2031.
Okay, yeah. So maybe before we go any further, I guess we should actually talk about what visually is probably the most distinguishing feature, the sort of long nose, which, if I understand correctly, was one of the technologies that has been able to reduce the sonic boom. Could you maybe talk a little bit about the physics and how this helps to reduce the noise?
Yeah, sure. Yeah. So, of course, sonic boom is the result of shockwaves. Shockwaves are instantaneous pressure changes that occur when an aircraft is flying faster than the speed of sound. Essentially, for normal aircraft, the subsonic aircraft, it's creating a pressure change, and essentially that's being communicated in front of the airplane, because pressure change is like a sound. It all travels at the speed of sound, so that's racing out in front of the airplane, and kind of the air is starting to get out of the way. Well, if you're going faster than sound, the air doesn't know the plane is coming, essentially. So you get an instantaneous pressure change called a shockwave, whether it's created by an airplane or a rifle bullet, it doesn't matter. Anything faster than sound creates an instantaneous pressure change. If you look at an airplane, anytime the flow is going over, it has to make a turn. As it goes over some part of the airplane, you create a shockwave. So there's a shockwave on the nose, near the airplane. There's a shockwave on the nose, there's one on the canopy, the engine inlets, anything that sticks out from the airplane creates a shockwave. So if you can visualize those shockwaves, which we can do, we've developed some really interesting technology. Of course, we've been able to do it in the wind tunnel for a while, but now we can do it in flight. You can actually see through what's called Schlieren imaging. You can see the shockwaves, and if you could see them, what you see is they're all different strengths, and they're all kind of randomly spaced along the airplane, wherever the components are. Because of that, because of the shockwaves of different strengths, as that signal, and again, that signal travels out in 3 dimensions. Some of it travels towards the ground, and that's what we're most interested in. But as that signal is traveling, because those waves are of different strength, they're actually starting to pile up on each other. So in a short distance from the airplane, all those shock waves have piled up into two. One, nose shock, what becomes called the nose shock, the first leading one, and then the tail shock. And that's a very stable acoustic system. It travels to the ground. It's getting attenuated. It's getting weaker and weaker as it goes towards the ground. But still, when it reaches the ground, you hear two very rapid pressure changes, which you hear as bang, bang, of a sonic boom. So what we found is the best approach, the approach that seems to work and can be integrated into a practical airplane, is to keep those shock waves from merging. So the whole shape of the X-59, that long nose, it's all designed to create a system of shock waves near the airplane where the shocks are relatively the same strength and relatively evenly spaced along the length of the airplane. So the initial system has all these shock waves in it, and because they're similar in strength, they don't merge as the signal travels to the ground. They just get each individual shock gets attenuated, and that's actually more of a benefit because you get down into the denser atmosphere, the shocks start to get smeared a little bit more. So by the time you get to the ground, you're left with kind of this gradual pressure rise instead of the sharp pressure increase. So you hear a thump or a thud thud instead of that very disturbing bang bang. So if you look at the X-59, it has a lot of features that we learned about when we did those airliner studies. The long slender nose sets up most of the forward part of the acoustic signature, if you wish. And then at the back end, you just kind of, it becomes much more complicated. So you're really trying to manage the shocks, and there's a little bit more than just having them be the same strength. You can kind of get them to cancel each other a little bit. So integrating the engine, so like the engine on the X-59 is mounted on top of the aircraft. So to prevent the shock wave from the engine inlet from kind of impinging on the bottom signature, the signature that travels to the ground. The tail of the airplane is kind of unique. On the X-59, we've got a little canard, we've got a conventional horizontal tail, and then a little T-tail. Each of those features helps us generate the lift we need and helps us trim the airplane, but minimizes the impact of those features on the sonic boom.
And it does look nice as well, I have to say. The aircraft actually looks quite nice, which always helps, right, I think.
Yeah, exactly right. Well, there's an adage in aircraft design that if it looks good, it is good.
Yeah. Of course, Concorde famously had to, tweak the nose for visibility.
Right.
How about on this type of design? What's the visibility, and for the pilots, what's their opinion?
It's bad. So we have a new approach. And thank you for asking the question, because it's really one of the unique features that NASA has contributed to the design of the X-59 is our external vision system. So rather than having a forward-facing window, we have a camera that sticks out from the nose. It's mounted on the forward fuselage, and it creates a high definition camera. It creates a high definition visual image for the pilot that's displayed on a screen in front of his seat. It's a really interesting technology. We've flown it in kind of demonstration flights on subsonic airplanes, and we found that it gives the cameras and the screens have reached the point where they can give the pilot the same visual acuity as they would have with their eyes looking through the window. We did a study where there was a pilot, flying the airplane, and then there was a pilot in the back looking at the screen, and we flew against opposing traffic, and it turned out that the pilot in the back could actually, would generally pick out the targets faster or earlier, further away than the pilot in the front. But that's not the end of it. I mean, if you've got this screen in front of you, you can mix the radar, infrared, other sensor features in to really improve situational awareness. For people who fly, you might not see an airplane, but when the air traffic controller says, you've got traffic, 12 o'clock, 2 miles, and you look in that direction, your chances of seeing it are much better than if you're just kind of, generally looking. Well, just imagine if instead of the controller saying it, the radar system put a little circle on your screen and said, hey, there's an airplane out here. You would always be able to see the traffic. So it's a unique technology. It enables the supersonic aircraft to be designed without having a complicated, heavy, nose-drooping system. But it's also something that could have applications in other types of aircraft as well.
How much is the pilot or the flying experience influencing the design? If you're a car, if you're designing a car, you actually think about driver comfort. You think about how easy it is to drive the car, to look out the window, to the experience. I always got the impression that planes were designed almost without any consideration for the pilot, but I guess that's maybe not true. I'm just wondering for this, how much you factor in the pilot's feedback and their needs.
So, human factors is a big part of aircraft design now, and I think, maybe when the first airplanes came out, there was less attention to just giving the instruments, but now I think that's a big part of how do you design the aircraft's instrument panel? How do you display information so the pilot can make maximum use of it, in a safe manner? One thing unique about the X-59 is it's an X-plane. So with the X-plane approach, the idea is we have certain key things that we want to demonstrate, and for an X-plane, you really want to make that as small a set of things as possible. So for us, it's all about the sonic boom. So besides the shape of the airplane is kind of a mishmash of parts from other airplanes. We've got F-16 landing gear, we've got an engine from an F-18, etc. So the X-plane, just try and make it work.
Yeah.
So we did not spend a lot of energy on human factors, but we did look at it. So we got our pilots involved early on. We knew we were going to have the screen, but we knew kind of beyond that, we kind of wanted it to look pretty much like a modern fighter aircraft inside as a single seat airplane. But the pilots got in. We have a really very sophisticated. We actually have two, one at Lockheed, one at NASA, really very sophisticated simulators. So that we put them in the simulators, with the cockpit design in there, and they were able to interact with it, give feedback, and then the design was updated, as we went along. So it's not a huge factor for the X-59. It's a big factor for actual commercial aircraft.
So I was actually wondering, as maybe a bit of a tangent, there's obviously a lot of discussion about computational fluid dynamics, reducing the reliance on wind tunnel technology. If you can do more in CFD, and I believe for this program, CFD was a big factor in being able to, iterate quickly and visually see what was going on. But I was actually wondering, you mentioned about simulators, because obviously normally there's wind tunnel to CFD, but then you have to do a flight test. You actually need to go out and do it. How much have simulator technology advanced that you can model some of the sort of flight test behavior through a simulator? Is that getting also more and more accurate compared to what it used to be?
Much more sophisticated. Yep. Again, for X-59, it's a unique airplane that the design will create some interesting some flight characteristics that are not typical of fighters or transports. So we really wanted to understand how how those things worked and how the pilot would interact with them. So getting a simulation. So there's so much simulation that goes on now. There's simulation without the pilot. There's simulation with the pilot. There's simulation without hardware, like the control actuators, and there's simulation with hardware. So the whole simulation process is a huge part of the aircraft design process right now. So for X-59, we did a lot of analysis. We did do some wind tunnel testing. There's still points in the flight envelope where the CFD is not all that great. So you like to augment your CFD analysis with testing. But compared to previous designs, we didn't do a lot of wind tunnel testing. As a matter of fact, we finalized the low boom design, the quiet boom design of the X-59 without doing a wind tunnel test of the geometry. So that's how far the CFD has come. We put all this stuff in the simulator. It's been iterated on a few times. So we're going into flight test with a very good idea of what the pilot will experience flying the airplane throughout the flight envelope.
Yeah, it is amazing how the technology has sort of moved on from that point of view. Just maybe I'm trying to think of a few questions, more practical questions. So the noise, as you say, going over, the idea is it's a sort of soft thump, which is less. It's something like we're used to everyday sounds, like I guess drones,
like distant thunder, or somebody's car door closing. We compare the sound to sounds like that.
But what about takeoff landing? I mean, you can go on YouTube now and look at Concorde it taking off, and it was an absolute racket, smoke billowing out of the engines. Like a real difference to like a normal aircraft. What's the, not for the X-59 now, but I mean more just for like theoretical design concepts? How much is the engine noise, because it's, as you say, it's not a conventional engine? How much is that different or a limiting factor?
It's again, we talked about it earlier. It's another kind of barrier technology that we've made a lot of advances in. The X-50, it's not an X-59. We're just using an existing engine, but as part of the bigger technology program in NASA Aeronautics, we call it the Commercial Supersonic Technology Project. Airport noise is one of our big efforts. So we're looking at the engine cycle. So we can't have a super high bypass engine, but at Mach 1.7 we can have much higher bypass, much more fan component than the Concorde did. So that's a major help. Our jet, the jet coming out the back of the engine at subsonic at takeoff is actually subsonic. It's not like Concorde was. The jet was coming out faster than the speed of sound, which creates noise, of its own. So our jet is subsonic. We've got nozzle technologies which mix faster flow with slower flow, so the aggregate results coming out the back end is slower. Then there's the whole idea of the propulsion installation. Can you use that to help reduce noise? So all of those things are being studied, and we think again we've done testing, but we think we've got a solution that can make supersonic aircraft as quiet as the current limits for noise for subsonic aircraft. So that's a big improvement relative to where Concorde was.
So I guess the big question on most people's minds is what do you think is the likelihood of a commercial version of this? What is there's obviously research going on, you're doing, there's companies like Boom, but from what I could gather, Boom, that design looked more like a traditional or more traditional design than what you have. I mean,
yeah. So Boone's approach is kind of unique. They wanted to, they see that there's a market now that they would like to capitalize. They've talked about their next generation of airplane incorporating boom shaping. Again, they don't want to commit to doing a design for a low boom aircraft without having a standard in place. As a matter of fact, they don't want to commit really to. Well, they've kind of committed, but they're working with ICAO, and the FAA is working with ICAO to put a noise rule in place for supersonic aircraft, landing and takeoff noise rule in place for supersonic aircraft. So that would give them that certainty. The work with ICAO really started because there was a group of companies that really felt that they could bring a supersonic business jet product, business aircraft product to market if they had a regulation on how loud it needed to be when it flew over land, or how quiet it needed to be when it flew over land. So there's definitely that market out there in the near term for a smaller aircraft. NASA's still bullish on if we continue down this path, there are technology solutions out there which could make it possible to design an airliner that could serve a supersonic market.
So what's stopping it? So let's imagine the rules come out and they are essentially aligned to what you already know from your simulations. Because I presume you already have an estimate, and all the flight test is doing really is proving it out. I guess you have analytical methods. So let's just assume that they agree with your numbers. Is the technology ready? Is it a case that a Bombardier, a Boeing, or whoever the company is can just basically do it? I know I'm massively oversimplifying things here. Or is there still something missing that is stopping them?
I think that for a smaller aircraft, a business type aircraft, the technology is very close. The key challenge really for a near-term product is the engine, because you need something that gives you the efficiency that you need, but will meet that new landing and takeoff noise rule. It's possible you could do it with a modification to an existing engine, change the front end, change the back end, but more than likely you're going to need a new engine, and that's magnified a little bit more for the larger product. You really need kind of a bigger step in technology, in engine technology, to be able to make the airplane meet noise and emissions limits for supersonic
by
flight.
Big and small, are you talking small being the 100-person 1.8
No, I'm
Mach?
talking small being the next step for Gulfstream, say an airplane that has room for maybe 8-10 passengers, or maybe up to 50, like Boom is imagining, or 40. I can't remember exactly where their target is, but so that's the smaller airplane. The where we're thinking about for the first generation of airliner products would be around 100-seat airplane.
Okay. So what I understand, you're saying that it's the engine technology in some ways that is the more challenging technology, and it obviously gets more important or challenging the bigger, the heavier that it becomes.
Think of it as a business jet can afford to be a little less efficient.
Yes.
Because there's people willing to pay for speed, but the airliner needs efficiency, quiet, and low emissions, which takes a new set of technologies. There's ideas out there. There's technologies at kind of the infancy level, but they need to be matured.
And is there any, you know how the economics work? When something aligns to something else, there's double the reason to do it. Is there any similar reason, like a military reason or another reason that aligns this, or is this quite unique in some ways for a passenger supersonic?
The military is not really interested in quiet. They would love to have supersonic speeds. They don't. It doesn't seem to be a major requirement for military missions, at the moment. Because if you look at what's out there now, the airplanes can go supersonic, but not very supersonic. They certainly don't cruise supersonic.
Yeah.
If they could do it, would they? Maybe. But they obviously other requirements, stealth and IR are kind of driving military designs, which the intersection between that and low boom design is not there.
So it really is. Would you say companies are just hedging their bet or waiting because they're just not sure when the rules will change, so it's almost hard for them to put the investment in to start designing something if they're unclear? Is that also one of the key barriers to it?
Yeah, it comes and goes. I mean, there was a lot of work going on a few years ago. Some of the companies have put those efforts on the back burner. Essentially, I would say yes, they're waiting for those regulatory guidance. That understanding of what their design requirements will need to be before they plunge back into looking at products.
So maybe, and again, this is always a common question. I must admit, I'm guilty of sometimes thinking the same, and you partially answered it before, but maybe we could be more explicit. If, let's say, the supersonic 1.8 Mach number is solved, so the new rules come out, there is sufficient economic reason for the engine manufacturers to do it, and a supersonic business jet comes out. In your mind, what's the technical or economic potential of a hypersonic passenger travel? Not 100 people, but 20, 30 people, Mach 5, Mach 6. Is that science fiction? Is it possible?
I wouldn't put it in terms of science fiction, but the challenges are much greater than for supersonic. You get to very high altitudes, and you get to very high temperatures when you get to Mach 4 and Mach 5. So, being able to design something that's reusable, that materials that will last for thousands of flights, and then then some of the safety considerations. One of the things that airplanes are designed for, in the event of a depressurization, there's a way to keep people, keep people alive until the airplane gets down. When you're up at 70, 80,000 feet, that's a huge challenge. So, I know NASA is. We have a hypersonics project. They're looking at hypersonics technology more from the point of view of what would it be for helping space launch. What would its applications be in space launch? But again, we had this whole study looking at is high speed flight a possibility? Peter's opinion is it's going to be a very long time before the technology is ready to even take 8 or 10 people into hypersonic flight. Who knows?
It seems
maybe the whole idea of orbital transport will come before hypersonic flight, because but again, getting people on board and making it safe and economical is a big step.
Yeah, I think the overriding thing for most people is, and I'm sure you feel the same, being so passionately involved in this project, there's always, normally we're used to technology adoption being a linear thing. Something gets faster, and we almost never go backwards, do we? The internet's got faster, computers have got faster. It's always a sort of peculiarity that we did go supersonic and we were doing it, and now we've sort of gone backwards. And I always, I guess that's why for most people, supersonic travel is such a intriguing thing, because they know it used to be. And I guess some people were lucky enough to fly in Concorde, and maybe they even more so wish it was still here. But for people like me, it's just a fascinating thing that we did it. And now, I guess it's like going to the moon. We did it, but we haven't been back for quite a while. But I guess that's also changing.
But it's yeah. I mean, space flight is the same thing. It was, we needed that technology. There was a space race. So, it was a stretch. The moon landing was a big stretch. Concorde was a big stretch, and maybe we stretched a little too far. Proved that it was practical, but for a supersonic flight, for example, revealed that there were some things which you have to create a balance. We like to go faster, but we can't disturb people's lives. Now we've got aircraft. Aircraft are going to have to be sustainable. They have to not contribute to climate change. So there's more things to weigh than just speed. Which again, kind of puts barriers in the way of reaching that goal.
One quick question before I completely change topic. Battery technology. It's always been. I remember for cars, there was a point when people said it was never going to be available for cars. Electric, they have a little golf buggy, and that's about it. There's no way it's ever going to be for a car. And yet, suddenly, the whole market started to transform, and it really felt like there was a step change in the adoption of electric. I haven't been following it as closely, but where do you see battery technology for aircraft propulsion? I don't mean complete electric aircraft.
I'm not a battery guy.
Okay.
But I will say that, in NASA Aeronautics, unique, new, sustainable propulsion systems are an area of intense interest. So we have a number of efforts looking at battery-powered electric flight for smaller aircraft. We have something called the Electrified Propulsion Flight Demonstration. It's an effort that's going on right now. There's two contractors, GE and MagniX. MagniX has built a number of electric-powered airplanes already, investigating what it would take to get there. Would it be battery? Would it be hybrid? Would it use fuel cells? All those kind of features towards making essentially non-combustion propulsion a viable option. There's a lot of work that needs to be done, but again, like you said, I mean, when people a few years ago, people couldn't imagine an electric car. People couldn't imagine a rocket that would come back and land on the ground. So never say It's you try to challenge yourself, to be realistic and think about what we can do in the near term, but you really should never say never.
Yeah, exactly. Yeah, being caught by some scissors, that probably wasn't on people's minds a while ago. So maybe the final question for you, which is, you've worked for NASA for decades now, I guess, maybe more than 30 years. What advice would you give to people who are looking to start a career in aeronautics? What I know it's probably a question you get a lot, but what would you be advised if you're somebody maybe in the final years of school, thinking about university, thinking about a career? What would be your advice to them?
Well, I mean, one of the things I always tell people, right now I got a degree in aerospace, aeronautical engineering, which, give me a unique set of skills, obviously, which got me into the aerospace business. There are other degrees, which you should, electrical engineering, mechanical engineering, all of those things can give you an opportunity to get into an aerospace field. For people in school, there's so many internship opportunities. I say, take any opportunity that you have to do that. Take it, because it gives you experience to help you figure out what you really want to do. It gives you exposure to how industry works, and you meet people who could kind of benefit with you when you start your career. Beyond that, where you get to work, be a team player, be willing to do something that puts yourself outside of your comfort zone. I was, pretty much a technology guy, very happy doing my little aircraft design work. My bosses kept pushing me to get involved in more of these multidisciplinary studies that were going on, and it was a challenge for me, to get out there and interact with people, but definitely gave me a skill set, which was, really very important as I got into the position where I helped create the program that eventually led to creation of the Quest mission. So, by being able to work with people and set common goals and set up an environment where you can achieve those goals. That was all part of the background. That exposing myself to things outside of just the typical math and science helped me help set me on that path.
And is there any in now, I guess, as the aerospace industry is changing and there's startups around, and do you think, how valuable is it for people to, for example, do a PhD and go down the more academic, becoming an expert, or how much of it is valuable to also gain sort of industrial experience? Would you, if you're looking at employing somebody, would you like somebody who's worked at different smaller aircraft manufacturers or companies and bring diverse skills, or would you tend to say to people, no, go down the more academic, doing a PhD or maybe becoming a research scientist? Is there any thing you've observed?
There's benefits to everything. Again, I talked about being able to work as part of a team. So to me, if I'm hiring people, someone who's had that kind of experience would be someone that I would look for, to bring forward. That said, we've got people, that have come to NASA from different higher education, from PhDs, from master's programs, and they're brilliant, so that puts them on the right path to begin with. They've kind of honed that knowledge. They've already maybe got this idea that they can do something new and unique, and you put them with a team that addresses all the other aspects of that new and unique idea, and that's how you get to breakthroughs. And that's a lot of what happened with the design that led us to X-59.
Well, thank you so much for taking the time to speak. I mean, what I think I'll do is I'll put a bunch of links for people to follow, because I know there's lots of videos and papers that have been published on these things that maybe people could dive into.
Sure. And of course, the NASA website, nasa.gov/Quest, 2 S's. There's all kinds of information about the project there. People can sign up for our boarding pass, which your name will be digitally carried aloft on the first flight of the X-59. And again, it's a great way to interact with get information about what's going on at NASA.
Great. Well, I certainly hope that I'll have the opportunity to fly in a supersonic aircraft, and I'm sure that if it does happen, it will most likely be thanks to the work that you and your team has done. So anybody listening to this should be thankful of the work that you and your team are doing, because it might help save us from 8-hour flights across to the US.
Yeah, we're just hoping. Again, it's important that whatever we do, the public buys into. So getting their opinion is all what Quest is about. But we do, for NASA, high speed flight is part of our the foundational things that we're working towards.
Yeah. Well, thank you again. Really appreciate it. It was great to talk to you, and good luck for the rest of the program.
Pleasure talking to you, Neil.